Um, okay, we are live. So, first of all, good afternoon, everyone. In the name of the entire directing board for the symposium and for the student association, I'd like to welcome you to our last conference of the day. It's my pleasure to introduce William Phillips, who's an American scientist awarded with a Nobel Prize in Physics in 1997 for having developed the methods to cool and trap the atoms with laser light, and for having invented the Siemens law, a technique to reduce the movement of gaseous atoms in order to study them in detail. Phillips is a professor of physics at the University of Maryland and head of the physics laboratory at the National Institute of Standards and Technology in the United States. So during this conference, we're going to stop halfway so that any questions you might have, we can answer them for a few minutes and they will continue. So if you want to send any questions, go ahead in the Q&A section. So without further ado, William Phillips.
Thank you very much for that kind introduction. It's a pleasure to be participating in this symposium, albeit remotely. I hope that there will be another time when I'll be able to visit for real. But for now, we have to be satisfied with these kinds of remote connections. As you've heard, I'm connected to both the National Institute of Standards and Technology, the National Metrology Lab of the United States, and the University of Maryland. And these two institutions together have formed a joint quantum institute, of which I'm also a member. But the thing I'm going to be talking about today really has to do with my connection to Nist, to the National Institute of Standards and Technology, where I'm a member of the Laser Cooling and Trapping Group. I'm no longer the group leader of that group. Gretchen Campbell has taken over that and is doing a much better job than I did. And my other colleagues, Paulette, Trey Porto, Ian Spielman, Ida Tietzinger, and Charles Clark are the people that it's a pleasure for me to work with on a daily basis. And also, I should say that not only is Nist bringing you this talk today, but also the International Union of Pure and Applied Physics, IUPAP, has been a promoter of the International Metric System, the International System of Units, since its beginning, and I'm a member of the Commission on Symbols and Units, and I'm spreading the word about this reform of the International System of Units. So what is the nature of this reform? Well, we have changed the International System of Units in a way that is more dramatic, more revolutionary than anything that has happened to it since the French Revolution, which was the beginning of the metric system. The modern metric system, the International System of Units, or the SI, is a system in which 7 base units, the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela, form the basis for everything that we measure. And the reform that we have undergone just recently is that now every one of the base units of the International System of Units are defined by fixing the value of some constant of nature. Now, in order to understand how this can be done and to see how it was done with an earlier unit, namely the unit of time, the second, and with apologies to the late, great Stephen Hawking, I'm going to bring you my version of a brief history of time. So ever since we have had seconds, the second was 1 over 24 times 60 times 60, or 1 over 86,400 of one day. That's what we mean by a second, or at least that's what we used to mean by a second. Because by the beginning of the 20th century, people realized that the rotation of the Earth was not constant, that it changed from time to time due to all sorts of things, like the tides slowing down the rotation of the Earth, like earthquakes and changing ocean currents would change the rotation rate of the Earth. And by 1900, there were mechanical clocks that were good enough to see this. And so around the middle of the 20th century, we began to develop atomic clocks that were far better than the rotation of the Earth. And this is a picture of the first cesium clock that was made at the National Physical Laboratory of the United Kingdom, their national metrology laboratory. And in 1955, they started operating this cesium clock that was much better than the rotation of the Earth. And so, since you had a technology that was considerably better than the very definition of what you mean by a second, it was clear that you had to do something. You had the ability to measure time far better than you could define what a second was. So it was clear there needed to be a redefinition. And so in 1960, they redefined the second to be a fraction of the year 1900. What were they thinking? It's true that the year 1900 never changes, but it's not readily available for measurement today. And so finally they got smart. And in 1967 and 1968, the General Conference on Weights and Measures adopted a new definition, an atomic definition of time, saying that the second was the duration of a certain number of periods of the radiation connected to hyperfine levels of the cesium atom. And that remains the definition of time today. And from the time that definition was made, back here in 1968 or so, well, the Essen clock was already operating before that, and the clocks have simply gotten better and better over time. And they got, in the mid-1990s, so good that they were better than a part in 10 to the 14, the best that anything could possibly be measured. But interestingly, those clocks weren't getting better than about a part in 10 to the 14 because the cesium atoms are moving so fast. Now, another thing that I've been interested in for a long time, namely laser cooling, which makes atoms go more slowly, addressed that problem, and it improved the performance of these clocks to a few parts in 10 to the 16. And here is a photograph of a clock, a cesium clock at Nist. There's Don Meekoff and Steve Jeffords, and they cool atoms down to about a millionth of a degree above absolute zero, launch them up in a vacuum. They come back down after about a second, and these clocks keep time to a few parts in 10 to the 16. By far, it is the most accurately measured quantity in the International System of Units. So here is a key idea about what has been done to the definition of time. We started with a definition of time that was based on the rotation of the Earth, something that was not a constant of nature, something that was a sort of an artifact. It just happens to be the Earth we have. There's nothing special about it. And they redefined the second in terms of the properties of a particular atom, the cesium atom in this case, a quantum definition, because the energy levels in the cesium atom are determined by the rules of quantum mechanics. So now we have a definition that's based upon a constant of nature. And this is a key concept in the evolution of the definition of the units in the International System of Units. So now I'd like to tell you another story, a short history of length. Time was important, but length was really important. And one of the reasons length was so important was because it involved commerce. And Mexico has a wonderful history of measurement and commerce. When Cortez came, he wrote about the standards of measurement that the Aztecs had, and said that they have measures for everything. This idea was captured in this wonderful mural by Diego Rivera. And one of the things that I find so pleasing is that one of the standards of length used by the Aztecs, unlike the standards used by the European, like the yard and the foot, one of the standards of length was in fact approximately equal to 1 meter. So it was really very modern what these pre-Columbian Mexicans were doing. Now, it was very convenient to have your standard of length based upon the size of the human body, because it meant that you always had your standard of length with you. The trouble was that it wasn't very consistent. If you were buying fabric from a short fabric merchant, you might not get as much fabric as you had expected. And this was a problem that everyone had. And so one solution was, let's specify a particular person's body as the standard of length. And in ancient Egypt, that was the length of the arm of the pharaoh. So the monarch's forearm was the thing that defined what was meant by a royal cubit. And that royal cubit was used to do all sorts of things like build the pyramids. But it was not very convenient to use the pharaoh's arm to measure the stones that went into the pyramid, and so instead they made an artifact standard. This piece of stone was made to be the length of the pharaoh's forearm. So this primary standard, very modern approach to things, became the standard of measurement for ancient Egypt. Now, the people in the field were not using this standard. They were using wooden standards that had to be recalibrated every month. And if you didn't calibrate them properly, you could be put to death. That's how serious they were about metrology in ancient Egypt. And it paid off. The baselines of the pyramid are consistent to a tiny fraction of a percent. They're square to 12 arc seconds. These pyramids were really well made because these people took metrology seriously. But this idea of making an artifact was common in many places. In lots of villages in Europe, you would have a length standard that was cemented into the wall of the town square. And here you see a standard for a fathom in the city of Regensburg. And it looks like it's a pretty good place to buy things by the fathom, because that's quite a long fathom, as you can see by comparison to a tourist who happens to be the wife of a metrologist. But the problem was that as well as this worked for people selling things in the town square of Regensburg, if you went to a different town nearby, you would have a different standard of length. So this was a common and annoying problem, that the standard of length varied from place to place. So now comes the French Revolution, the beginning of a new approach to measuring things. And the French revolutionaries decided that in the spirit of brotherhood and equality and fraternity, that they would have a new standard of length that would be available to everyone, that would be universal. And they defined this new standard of length, called the meter, to be 1/10,000,000th of the distance from the equator to the pole on a meridian going through Paris, just to ensure that it was completely universal, you understand. So they sent out surveyors to determine the distance between Barcelona and Dunkirk, a fraction of this meridian. And then, knowing something about the shape of the Earth, they were able to extrapolate to the full length of this meridian. And these surveyors came back and reported their results, and people felt that they had really achieved a revolutionary dream, that they had created a standard that was good for all time, for all peoples, à tous les temps, à tous les peuples. And they cast a medal to commemorate this idea. And you see this medal here. And on the one side of the medal, you see a mythological creature, an angel-like creature, is actually measuring the Earth with calipers. Well, that's what they did with these surveyors, was they measured the Earth. And they brought back what that measurement was in the old measurement units. But while it was stable and to some extent universal, this measurement of using the Earth was not very convenient, just like the pharaoh's forearm. And so they made an artifact, just as they had in ancient Egypt. And here's a picture of that artifact. This is called the Meter of the Archives. And it was placed into the archives of France in the year 1799, a platinum bar. And from one end to the other of this bar became the definition of the meter for the country of France. Some decades later, an international conference called the Convention du Mètre, the Treaty of the Meter, decided that the meter would become universally used by all the countries of the world who were participating. And they made a new meter bar, a new artifact standard. And this one was made of platinum iridium. And you see its shape here. Here's a photograph of a few of the copies. And here, the meter was the distance between two scratches on this bar. And it was made to be as close as they could make it to the old meter of the archives. But now you had a somewhat better standard because you didn't have to touch the ends. And when you touch the ends, they get worn down, and people were worried about the standard changing. So they had this thing that was 1 meter between these two scratches. Well, almost immediately after having this definition, people realized that there were better ways of measuring length that could actually measure length better than the standard of length could define what you meant by a meter. And that better way was using light and the interference of light, because they had discovered all throughout the 19th century that light was a wave, and you could interfere one light beam with another, as you can see in this cartoon of a Michelson interferometer, that a beam of light going in this direction, bouncing off this mirror here, coming back and reflecting from this beam splitter, would interfere with another beam of light going in this direction and reflecting from the beam splitter and bouncing off that mirror and coming back. And it would produce an interference pattern like you see here on the left. And the beautiful thing about this is that if you moved this mirror 1/4 of a wavelength of light, that's 1 fraction of a millionth of a meter, then this interference pattern would change from having a dark spot to having a bright spot at the middle. This was to be compared against a scratch. The scratch was many micrometers wide, and it was a scratch. How did you know where the middle of a scratch is? You look at it with a microscope and you have to decide, where is the middle of this scratch? And so people could not realize the definition. They couldn't define what a meter was, as well as you could measure length using this interferometric technique. And so, just as in the case of time, you now had a technology for measuring length that was better than the definition of length itself. And so finally, it took them a while. In 1960, the year in which the laser was invented, they decided that the light from this krypton lamp would be the new standard of length. People had been using the wavelength of light from lamps as a kind of de facto standard of length for decades because it worked so well. Now they finally changed the definition of the meter so that it was in fact a certain number of wavelengths of light coming from a lamp like this one. But almost as soon as that definition became the legal definition of the meter, people realized that there were better light sources. This is a picture of a helium neon laser. It makes a red light that is extremely pure, much more pure than the light coming out of the krypton lamp, and stabilized to a certain optical transition in the molecule iodine, diatomic iodine. And this became the new de facto standard of length because it was a technology that was clearly better than the krypton lamp. So again, we had a situation where the technology made it possible to measure length better than the definition of length itself. And so it seems we needed to change the definition again. And the obvious choice would have been to redefine the meter in terms of the wavelength of light coming out of an iodine stabilized helium neon laser. That would have been the obvious thing to do. This source of light was already being used as a de facto standard. But fortunately, they did not do the obvious thing. Instead, they did the brilliant and beautiful thing. They defined the speed of light. This simple equation says that the speed of light is equal to the wavelength of light times the frequency of light. So if you can measure the frequency of any light source, and if you define what the speed of light is, you immediately know what the wavelength is. And so in 1983, they said that the meter was the length of path traveled by light in 1 over some very large number, some fraction of a second. And this number here is, by definition, the speed of light. And the beauty of this definition is that if people learn how to make better sources of light that are even more pure, and they did, the definition is still good. And if people learn how to make better frequency measurements, and they did, the definition is still good. And so this illustrates a really beautiful concept now, that the meter went from being an artifact to being defined in terms of a constant of nature that involved a particular atom, to a definition that involved a fundamental constant of nature that's not tied to any particular atom at all, namely the speed of light. And the beauty of this is that we should never have to change this definition again, even when we improve the technology, as we have been doing ever since the definition was adopted. And now we are faced with the possibility of changing the definition, not only of the kilogram, but of the ampere, the Kelvin, and the mole in this same way, in this beautiful way. And on the 20th of May, the international community brought this new idea, this beautiful idea of defining things in terms of a fundamental constant of nature to all of these units. Why was it necessary to do this now, and how was it done? Well, in order to give you an idea about that, I'm going to bring you a light history of mass. So, in ancient times, as we've seen so many times before, we had artifacts, and we had artifacts for mass. These are a set of polished stones that were used in ancient Babylonia, and similar artifacts were used elsewhere, manufactured objects that were the standards of mass for all of Babylonia. One of these things, I forget which one, is called a shekel. You may have heard that as a unit of mass, but it suffered from the same problem that all the other artifacts had, that if you had copies of these things, they might be different in different places. And if you went to a different country, they would have a completely different system of units. And so at the time of the French Revolution, our revolutionary metrologists decided that they would also have a universality for the unit of mass based upon the unit of length, the meter, which was to be the measure of all things. And what they decided was that this new unit of mass, called a kilogram, should be equal to the mass of 1 cubic decimeter, what we call 1 liter, of water. So this was wonderful. Water is universally available, and the meter was well defined, but it turned out it wasn't that easy. It turns out that the density of water changes with temperature, so that's a problem. Water sticks to some surfaces, and it doesn't stick to other surfaces, and so the meniscus that a water forms when it meets a surface can be different depending upon the nature of the surface. And it was just very difficult to measure what a kilogram was using this definition. And so what did they do? They did what they'd always done. They made an artifact. And here I am with that very artifact. This is the kilogram of the archives, a piece of platinum that was deposited in the archives of France in 1799 that was a mass as equal as they could make it, as precisely as they could make it, to 1 liter of water. And then this replaced the old definition of mass based on a liter of water. And when the countries of the world got together in 1875 to sign the Treaty of the Meter, they agreed to make a new mass standard, this one made of platinum iridium, and it's pictured here. It's almost exactly the same size as the kilogram of the archives, and they made several copies, many copies, in fact, for everyone who was a member of this original Treaty of the Meter. And the one that was closest to the mass of the kilogram of the archives became the international prototype of the kilogram. And it's shown here under 3 bell jars. Here's a picture of me in front of those 3 bell jars. You have to go down into a sub-basement of the International Bureau of Weights and Measures, and they have to use several different keys to open the vault where this is kept. And we just got to look at it. It only comes out every few decades. It's really a very sacred object, it seems. So that was, and still is, or still was, I should say, until the 20th of May, 2019, the definition of the kilogram. Now think about this. In the 21st century, the unit of mass was an artifact, a piece of metal that was made in the 19th century that was based upon an object that was made in the 18th century. That in the 21st century, we should be using this as our definition of mass is such a scandalous idea that, in fact, American newspaper comic strips were making fun of it. So in this comic strip, a little girl who's inside this schoolhouse is asking her science teacher, "Isn't it true that we have redefined the meter to be based on the distance traveled by light in a certain fraction of a second?" And the science teacher answers, yes, because the old definition based on global distances was inaccurate, as we've seen in what we've studied so far. And she asks, and in the same way, we've redefined the second, which used to be a fraction of a solar day, but now is defined in terms of a cesium atom. And he says, yes, very good. And then she says, then why haven't we redefined the kilogram? The kilogram is still the mass of the international prototype of the kilogram, an actual lump of stuff that's stored somewhere. Isn't it beautiful that a newspaper comic strip is talking about metrology in such a serious way? She says, what if somebody sneaked in and shaved off a piece of the kilogram? And this disturbs her science teacher so much that he has to lie down, and she has achieved her objective of getting to her teacher. Well, nobody has sneaked in and shaved off a piece of the international prototype of the kilogram, but it appears to be changing nevertheless. Here is a plot of the mass of a number of copies of the kilogram made at the same time as the international prototype of the kilogram, made to be as identical as could possibly be made to the international prototype of the kilogram. And this shows their mass over time. And you can see that they're all pretty much going in the same direction. Well, if you think about it for a while, you think maybe it's the international prototype of the kilogram that's changing. But of course, the international prototype of the kilogram cannot change because by definition, it is a kilogram. If I were to touch it and leave a fingerprint on it, all of you people would lose weight. This is an absolutely intolerable situation. And so we have to fix it. And before we understand how we have fixed the kilogram, let's see if there are any questions up until this point.
Yes, we have some questions. First of all, is in 1835, when they use a rod to measure the meter, doesn't the meter change with temperatures, being that it expands with heat and shrinks with cold?
Absolutely. So there's an additional little part to the definition, what they call in French, because everything was done in French, because French was the international language of diplomacy at the time. So they call this a mise en pratique, the way in which you put into practice the definition. And so the length that is defined to be a meter is the length of between those two scratches at a certain temperature. And I'm not sure whether they specify the humidity and the pressure. It probably doesn't make much difference. It's mainly temperature, but the temperature is specified. And I think it's 20 degrees C, but I can't really remember.
Thank you.
But of course, that's another one of the reasons why it's a problem,
Sure.
because it means you've got to control the temperature, and the degree to which you don't means that you don't know what a meter is.
Thank you. We have another question. How can you define the meter with a number that uses meters per second as a unit? Isn't that like defining the meter with the meter itself?
Well, it's a good question, but you have to think about it very carefully. The meter, the way the definition was written was the meter is the length of path traveled by light in a certain fraction of a second. So in that way of stating what the meter is, you do not use meter in the definition. Now, in the new formulation, where all of the units of the SI are defined by defining a value of the of a fundamental constant, we could say the meter is that length that makes the speed of light equal to this in meters per second. So you see the spirit of that? It's really the same thing. It's not a circular definition. And I think you can see why it's not a circular definition by looking at that original definition that says the meter is the length traveled by light in a certain amount of time, and then realizing that what that definition does is define the speed of light.
Thank you. Another question. Do you think that making the meter definition dependent of time is a good idea? What if the definition of time changes over the years?
Well, that's an interesting question. And I think the definition of an interesting question is one that doesn't have a very good answer. So right now we have defined the unit of time to be such that a second is a certain number of periods of the transition frequency between two levels in a cesium atom. So now you may ask yourself, what if that changes? But then think about that. It can't, because that's the definition of what a second is. And in the new way of doing things, we've defined the frequency of that transition. So asking, what if the frequency of that transition changes, isn't a proper question, because it cannot, because the law says that the frequency is that big. Just like the law said that the length of the pharaoh's forearm was 1 cubit. If the pharaoh's forearm shrank, it was still a cubit by law. So it's a funny situation, but it's such a good question. So let me go a little bit further in talking about this question. Let's say that we have another atom, rubidium, great atom, also has a hyperfine frequency, and I could measure its hyperfine frequency in terms of the cesium hyperfine frequency. In effect, what I've done is measure the ratio of those two frequencies. Each one of them are, we believe, a constant of nature. But of course, we can't tell for sure whether they're constant, because the definition of frequency is based on the frequency of the cesium atom. But what if the ratio changes? If the ratio changes, that means we don't understand physics. And that would be wonderful, because if something as amazing as that happened, if something as fundamentally different about our understanding of nature, right now we believe that those frequencies should keep the same ratio no matter what. And if they don't, then we've got to come up with new theories of the way nature works. Now, people have been checking it, and so far, it doesn't change by even 1 part in 10 to the 18 per year. Now, it's not done with cesium and rubidium because we can't measure them to a part in 10 to the 18, but with other transitions in atoms where we can measure to a part in 10 to the 18, people have checked that the ratio doesn't change even to that level. So far, it looks like we do understand things, but it might be that we don't. So if we don't understand things, then we've got a lot of fun ahead of us.
Excellent. Now we have another question. If the English system is redefined, or is it, does it stay with the international convention?
Yeah, the so-called English system of units, whereas, of course, the English have pretty much changed over to the metric system. The United States is legally on the metric system. In fact, we were one of the original signers of the International Treaty of the Meter. So the simple answer is the so-called English system, the inch, is defined in terms of the metric system. There is no independent standard for an inch in the United States. An inch is 2.54 centimeters. Whatever the definition of the meter is, then the inch will always be that same fraction of a meter. And the same is true of all of the other so-called English systems of units. They're defined in terms of metric units. There are no independent standards. There's no standard pound. There's no standard foot. It's all done in terms of metric standards.
Excellent, thank you. So we have another question. Yeah, we still have a couple of minutes. How can you measure the speed of light, and how do you know that the velocity of light is the same in different directions? I mean, the only way that the people manage to measure the speed of light is for a round trip, and no one ever managed to measure the speed of light in just one direction. And I know that,
yes.
that they have to see in one direction in instantaneous on the return journey. How do you know
Yeah.
that this?
Yeah, this is a very good question. Obviously, this is a question from someone who understands a lot about metrology and about the kinds of tests that that can be done to find out about whether we understand the laws of physics, in particular the laws of relativity, well enough. So, while it's true that we cannot measure the speed of light, in fact, you might say it's illegal to measure the speed of light because it's defined, we could ask ourselves whether the speed of light is different in different directions. That's one of the things that the Michelson-Morley experiment was doing. It is the same in different directions as far as we can tell. There's also this issue about the one-way velocity of light, and that's much harder to do. And so the one-way velocity of light it's not been confirmed that the one-way velocity of light is not different in different directions, as well as the two-way velocity of light, the forward and back. Because if you remember that picture of the interferometer, the light was always going both forward and back along those same paths. So certain kinds of things might cancel out. Now, we have no reason to believe that the one-way velocity of light should be different from the two-way velocity of light, but good metrologists want to check anyway, because this is how we sometimes discover that things are different from the way in which we imagined that they were. I don't know that the redefinition of any of these units is going to help us to design better experiments to, for example, look into the question of whether the one-way velocity of light is different from the two-way velocity of light. But maybe. But it's the kind of experiment that I'm always happy to see. And I'm always looking forward to people coming up with new ideas for how to do these kinds of measurements better. So far, everything turns out to be okay.
It would be quite an interesting development if it turns out that it's not see both ways.
Yeah, it would be an extremely interesting development. And don't know what we would do. That is, the theorists would have something to work on that should keep them busy for a long time if it turns out not to be the same.
Final question for this section. Don't worry, we'll still be answering questions at the end, but this is the final question so that we can move on. This announcement is for everyone. Wasn't the Kelvin already defined as absolute zero? Did it still have a redefinition in 2019?
Okay, we'll get to that. So if you'll just wait a little bit, we'll talk about how the Kelvin was redefined from what it used to be before the 20th of May and what it is now. So we'll get to that, okay?
Okay, excellent. So let's go ahead and
okay, right. Okay, so let's see how we're going to fix the kilogram. Okay, Now, when we defined the meter, we used this beautiful definition. We defined the speed of light. So we're going to do the same thing with the kilogram. We're going to define a constant of nature. Which constant? Well, to think about that, to understand why we've chosen the particular constant of nature that we have, remember this equation, which I think is the most famous equation in all of history. E equals mc squared, where E is the energy of an object at rest, m is the rest mass of that object, and c is the speed of light. Now, here's another equation, not quite as famous. This says the energy of a photon is equal to the frequency of the photon times Planck's constant. So if we have a single particle of light, a photon, and we know its frequency, and if we define Planck's constant, then we know what its energy is. So we're going to make these two equations equal to each other and solve for the mass. And what you see is that the mass, now I'll say what that means in a moment, is equal to Planck's constant times the frequency divided by the speed of light. So what I mean is, if I had a mass like an atomic nucleus and it emitted a photon like a gamma ray, and I measured the frequency of that gamma ray, then the change in mass of that nucleus would be Planck's constant times the frequency of the gamma ray divided by the square of the speed of light. And you see, if we've defined the speed of light, and if we now define Planck's constant, and if we measure the frequency of the gamma ray, that means we have a way of defining mass. Now, we don't actually do it that way. We don't weigh photons. We can, it's just not done well enough to satisfy the needs of modern metrology. So instead, we use a different method, an electromechanical device invented by this guy, Brian Kibble. We now call it a Kibble balance or a watt balance. And this movie is going to try to explain how it works. So first, I want you to remember, how do we determine the mass of something traditionally? Well, if we have an unknown mass over here, we put known masses on the other side of the balance until it balances. Oh, it wasn't supposed to do that. It was supposed to. Okay, so I'm going to switch over. I apologize, but I'm going to figure out how to do this and get back my, oh boy, this is bad. I'm not getting back my arrow. Would you like to? Okay, boy, I don't even know why I'm getting this this dialog box, but let's go back to finding out. Okay, well, here we go. There we are. Now I'm going to go back to the arrow, and now I'm going to start the movie. Okay, and now I'm going to point to things with the arrow. Okay, so as we've said before, the traditional way of weighing something is that we have an unknown mass on one side of the balance, we have known masses on the other, and when the known masses cause the unknown mass to balance, then that means that we've determined the mass of the unknown object. Now, I want you to imagine for a moment a different way of doing it. What if, instead of putting masses on this side, known masses, what if I put a coil of wire on that side? And I put into that coil of wire current. And I put that coil of wire into the magnetic field of some magnet. Now, if I measure how much current is in this wire, if I know where all the wires are, so that I know the geometry perfectly, and if I know what the magnetic field is, and I know what direction it's pointing, then I can calculate what the force is. And I can use that force as a way of determining what the gravitational force is on the other side. And if I measure the acceleration of gravity, then I've got the mass. That would be another way of doing it. It would be a bad way of doing it, because I can't know very well where the wires are. It's very difficult to know how strong the magnetic field is and in what direction it's pointing everywhere. And so this is not a good way of doing things. And here's where the genius of Brian Kibble comes in. Kibble said, let's do another experiment. Let's take that same coil and take the leads of that coil and open up those leads and connect them to a voltmeter. Now, when you move the coil in the field of this magnet, it will create a voltage. And if you measure that voltage and measure the velocity of the coil, we call this the velocity mode, okay? Then that will give you all the information that you need to calculate the things you need to know about the force. And so you do this measurement, moving the coil in the presence of the magnetic field, measuring the velocity, measuring the voltage. Then you do the other part, where you put a current in there, you measure the current, and you balance that current against some gravitational force of your mass that you want to determine. Now, how does this all work? Let's look at this. We take the mass. That's the mass from the, let me go back to using the laser pointer. Okay, so we take the mass. That's the one that's the unknown mass. We multiply it by the acceleration of gravity. We multiply it by the velocity that we got when we measured during the velocity mode of the experiment. Okay, so we've got mgv. One of the variables comes from the force measurement, the weighing mode, and the other one comes from the velocity mode. On the other side is the current that we got from the weighing mode and the voltage we got from the velocity mode. So each side of this equation has one piece of information from the weighing mode and one piece of information from the velocity mode. And now I'm going to say they're equal because mechanical power, which is force times velocity, has got to be equal to electrical power, which is current times voltage. In any proper system of units, the power has to be equal to power. It is as if we made a perfect motor generator. The force part of the experiment is like running a motor. The velocity part is like running a generator, but there's no loss because the motor isn't moving and because the generator isn't moving. Everything is done statically so that we, or at least I should say the generator isn't drawing any current. So there's no loss. So everything is perfect and these two things have to be equal to each other. So we solve for mass and we find that the mass is equal to the current times the voltage divided by the acceleration of gravity times the velocity. Now, remember, I promised you that this was all going to be related to Planck's constant. So why is it related to Planck's constant? Because of the way in which we measure the current and the voltage. We have quantum ways of measuring current and voltage due to the von Klitzing effect, or the quantum Hall effect, and the Josephson effect. So here you see Brian Josephson, and here's Klaus von Klitzing. Brian Josephson told us that if I put a voltage across a Josephson junction, I would get a frequency that would be in have a value of 2A/h hertz per volt. And Klaus von Klitzing taught us that if we had a certain kind of semiconductor device, a two-dimensional electron gas, that the transverse resistance would be h/e² in ohms. And that means we can measure voltages and resistance in terms of Planck's constant and the charge on the electron. So when we measure the voltage over here, it's going to be in terms of h/2e. And when we measure the current, that's got to be equal to voltage divided by resistance. And the resistance is h/e². The voltage is 2A/h, so that the current is proportional to E. That cancels out the E here. And the mass is proportional to Planck's constant, just as I promised. So this kind of a balance, and here is a photograph of the balance that we have working at Nist, can realize the definition of the kilogram to a part in 10 to the 8th, which is better than the amount by which the kilogram appears to be changing because of whatever it is that's making it change. I just call it dirt. We don't know what it is because we can't really study it until now that we have a new definition of mass. And so here are some of the heroes at Nist who have done this job with the Kibble Balance. They are so serious about their metrology, just like the ancient Egyptians were, that they tattooed the values of the fundamental constants onto their arms. So these are the new values of the fundamental constants that define the new international system of units. Now, one of the beauties of using this kind of a definition is that it doesn't tell you how you have to use it. All it says is that Planck's constant is equal to a certain value. And there's another way that involves making the world's most perfect spherical object out of single crystal silicon isotopically pure. And that's what you're looking at right here. And if you want to ask me about it in the question period, we can go into how this works. But this is a completely different way of realizing the definition of mass, but it still uses the definition of Planck's constant. So here is a map of the world showing various places around the world where Kibble balances and perfect silicon spheres are being used to realize the definition of mass. And when everyone agreed about what the value of Planck's constant was, you see, because before they redefined the kilogram, this experiment was really measuring Planck's constant. Now that we all agree what Planck's constant is, we fix the value to be the value that they all measured. And now that's become the definition of the kilogram. So that's not all. Remember, I promised you the ampere and the others. The ampere used to be the current, which in two infinitely long straight wires, 1 meter apart, would produce a force of 2 times 10 to the minus 7 newtons per meter. Now, the ampere is defined by defining the charge on the electron. So an ampere is just a certain number of electrons per second. By the way, this definition defines the magnetic permeability of the vacuum to be 4 pi times 10 to the minus 7, I forget what the units are, newtons per ampere squared. That's no longer true. So if you've been teaching your students that mu naught, the permeability of the vacuum, is equal to 4 pi times 10 to the minus 7, it's not true anymore. It has to be measured today. Now, it's not going to be much different. It's only be different by a part in 10 to the 8th or so, but it's not by definition 4 pi times 10 to the minus 7 anymore. The mole used to be that the mole was the amount of substance that had a number of microscopic entities equal to the number of carbon-12 atoms in 12 grams of carbon-12. Now we have simply defined Avogadro's number. So that means the atomic mass of carbon-12 is no longer 12. It has to be measured because we've defined Avogadro's number instead of using the carbon-12 as a standard. And finally, the question that was asked, what about the Kelvin? The previous definition of the Kelvin was that it was 1 over 273.16 of the triple point of water. The thermodynamic temperature of the triple point of water was defined to be 1 over 273.16. Now, to make it more universal, we've defined the Boltzmann constant. Now, how was this measured in the past? It was measured by ideal gas thermometry, and that's the same way it's being measured today. And what that means is you measure the universal gas constant, and that's the way in which you determine what a Kelvin is, because you measure the universal gas constant at a certain temperature, and now you know what a Kelvin is. Well, you had to reference that to the triple point of water. Well, now the difference between the Boltzmann constant and the universal gas constant is just Avogadro's number. And Avogadro's number is defined. So it's the same thing, but now it's done in a more fundamental and universal way. But ask me about it in the questions if you don't like what you're hearing so far. Okay, so now the French Revolution brought us the metric system. And now we've been refining the metric system to the point that on the 20th of May, which was the anniversary of the signing of the 1875 Treaty of the Meter, we had this tremendous revolution in measurement, biggest revolution since the French Revolution, in which all of the units of measure are defined by fixing the values of fundamental constants. You can keep the international system of units in your wallet, just a card that tells you what the values of the constants are. And so it seems that we have realized the dream of these French revolutionaries, that we have a system of units that's good for all time and for all people. And so let me play this movie from the General Conference of Weights and Measures in Versailles, France, in 2018, this was when the General Conference voted all the countries of the world, 60 countries around the world who have signed on to the International Treaty of the Meter and are supporting the international metric system. They all got together and agreed to change the definition of the SI to go into effect on the following 20th of May. And this is what we saw after that historic vote.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world scientific community.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it.
Ce l'abbiamo fatta. Wir haben es geschafft.
Lo logramos.
没下伯利，
我们做到了。
Biz buna nail olduk.
Proud of that.
we worden just hadden. Het is ons gelukt.
We сделали это.
Fantastiskt.
Vi gjorde det.
Amerika.
Mi smo to učinili.
Dokázali jsme to.
سويناها.
Congratulations. 축하합니다. Felicitaciones.
Mazal tov.
Congratulazioni.
Shatera le lavorisce.
Selamat sukses.
Parabéns.
Ongela. Omedeto.
Amguida.
Onneksi olkoon.
Mabruk.
Kapai.
Aiko.
Félicitations. Congratulations.
Whenever I see that, I still become a little bit emotional, because when was the last time that 60 countries of the world could agree on anything? Unanimous agreement. And it gives me hope that if the countries of the world can agree on something as revolutionary as this change in the system of units, perhaps there's hope that we can agree on other things as well. And so it seems that we really have realized the dream of the revolutionaries, but maybe not, because time itself is still a problem. It is tied to the definition of a transition in a specific atom, cesium. And today we have the same situation that we have faced so many times in the past. We have other atoms with transition frequencies much higher than the 9 gigahertz transition frequency of the cesium atom. Frequencies that can be measured far better than the few parts in 10 to the 16 that we can do for cesium. Instead, we can do even better than 1 part in 10 to the 18 with these atoms ticking at optical frequencies. And so it appears that we still have something left to do, that we still need to define the second to take into account this newer technology, just as we've had to define the meter in the past and the kilogram in the past and the second in the past. We have to define the second again. And so we come to the end of this talk, but it's not really the end, because the SI second needs to be redefined. Thank you very much.
Thank you so much for everything you had taught us today. It was such an interesting topic that one doesn't normally think about, but in really it affects our daily lives. So thank you. First of all, I'd like to thank you from everyone involved in making this possible. Thank you for giving us some of your time and for coming with us here today.
You are very welcome. It's been a pleasure.
So let's start with questions. Some we have left from the first part. So let's begin. As a fun hypothetical question, if I wish to a genie to lose weight in the previous definition of the kilogram, the modification of the IPK would still be valid for me to lose weight?
Well, yes, if we were in the situation where the IPK defined the kilogram, and if some contamination got onto the IPK so that it became effectively heavier, and we couldn't get it off by the standard washing procedures. There's a mise en pratique for the kilogram that has it be washed in a particular way. Then everything else in the entire universe would have a lower mass. Now, the amount by which that would happen, those contaminants are not very big. They're on the order of parts in 10 to the eighth. So it's not like you would notice it, and it wouldn't be any good for your health to lose weight that way. You wouldn't have any fewer fat cells in you because you lost weight that way. But I just say that to illustrate how silly it is to have an artifact as the standard of mass.
Thank you. So now more anecdotal maybe. Do you know of any serious issues, anecdotes maybe in science, communication, or engineering arising from the not so ideal previous definition of time, length, or mass?
Well, yeah, certainly when it came to time, it was clear that when time is defined by the mean solar day, it was clear that this was an inadequate definition, that for example, you could not study the way in which the rotation of the Earth was changing. And this is a useful thing to study for planetary science. You couldn't do it because you didn't have a standard that was, by definition, able to measure it, because it was the Earth itself. Once you knew that it was changing, you'd like to study that, but you didn't really have the proper standard to do it. So we changed that. Now, for a while, of course, people were using de facto standards. So it's not often that you have a problem that you've got the technology, but you can't study the thing that you want to study scientifically. You just use a de facto standard, you study the scientific thing, and it's just embarrassing that you're not using the legal definition of a second to do it. But before we had that technology, what it meant was we didn't know that the Earth's rotation wasn't constant. People had this idea that the Earth's rotation was perfectly constant, and it was not. And we learned all kinds of things, like that earthquakes change the rotation of the Earth. They change the moment of inertia of the Earth. Well, it wasn't something that could be studied until we had the technology. So it wasn't so much the definition that mattered, although having the right definition certainly makes things a lot more convenient. And in some cases, it makes it easier to measure as well. But certainly there's one case where knowing about where the technology meant there were things we couldn't know about. Another one has to do with the recent redefinition of mass. It turns out that with the new definition, it's going to be a lot easier to measure small masses. The reason is that if you want to have a 1 milligram standard mass, you have to start with a kilogram, make 10 100-gram masses and compare them to the kilogram and see how they compare to each other, then make 10 10-gram masses. I'm not saying it's done exactly this way, but just to illustrate the idea, going all the way down to a milligram, and you lose a tremendous amount of accuracy in doing that. The new definition does not require that you do that because it's not based on a particular artifact. So measurement of small masses is going to be a lot easier with the new definition.
Thank you for your insight. Okay, now, do you think that if we encounter a stellar civilization, they would have a similar definition of measurement?
Yeah. Well, yeah, I love this question. Our definition now means that if we were to encounter another civilization, let's say we were to start to communicate by radio signals with another civilization, we could explain to them what we mean by a meter in a way that it would have been impossible to do back when the meter was defined in terms of the size of the Earth, or even in terms of the size of the meter bar. How would you be able to tell to these extraterrestrial beings who are many light years away from us, for example, what you mean by a meter when the meter is defined by a rod that is stored someplace? But when we say, and we assume because we have no reason to believe otherwise, and we have good reasons to believe that it's true, that the laws of physics are the same throughout the universe. Now, again, as we discussed before, that might not be true, but everything we know tells us that the laws of the universe are the same throughout the universe. And therefore, if we say a meter is the distance that light travels in a certain number of cycles of some atomic transition, and then they would know what a meter was. So we could describe how big we are, and they would have an idea of how big we are. We could explain how big the houses are that we live in, and how big the cars are that we drive around in, and how fast they go. Whereas if we didn't have this way of defining those units, we wouldn't be able to tell them those kinds of things.
Thank you. Now, in regards to the Kibble balance, in the Kibble balance, aren't you limited by how precisely can you measure G? Do you need a gravimeter to calibrate your balance?
Yes, you need to measure G very well. Now, it turns out that G is not the limiting factor, but it's close to being the limiting factor. So fortunately, there are very good ways of measuring the acceleration of gravity. In fact, there are a couple of nice ways of measuring the acceleration of gravity. You can drop a mirror, actually a cube corner, that acts as one arm of an interferometer, and then you measure the fringes and time them, and you can extract the acceleration that way. And you can do the same thing by dropping atoms and measuring their acceleration by measuring the Doppler shift of transitions in those atoms. And people do it both ways, and they measure the acceleration to a few parts in 10 to the 9. So when we're still working at a part in 10 to the 8th, it's not too bad, but we'd like to do better. So I'm hoping that in the future, we improve the acceleration of gravity. And this is a good motivation for why we should be working on improving the acceleration of gravity.
Thank you. Now, for a bit more personal question, what is the greatest challenge you faced in your scientific career?
Oh, oh, that's a good question. Okay, so remember, I told you that a good question was one for which I don't have a good answer. So let me answer it in a way. You see, if you ask me the same question tomorrow, you might get a different answer. So let me answer it in a very personal way. One of the very big challenges that I faced was, how am I going to balance the time that I spend on my career as a scientist and the time that I spend with my family? I know a lot of physicists, fortunately not so many, but I do know some physicists who, because of the way in which they have been devoted to their practice of physics, have become disconnected from their families. So I tried not to do that. I would always go home in time to have dinner with my wife and my children, and to put my children to bed. And then I would go back to the lab and keep measuring, because sometimes you have to measure all night because sometimes night is the only time when it's quiet enough to get that data. But I would always go home and spend that time with my family. And that was a tough thing, because I knew that there were a lot of other people working on the same kinds of things who were spending more time in the lab than I was.
Thank you. I think that was a really good answer. Thank you very much. Good. Do you think the metrologists will eventually reach a limit for the accuracy of the second? If so, will that limit be relevant to our physical models? For example, reaching a limit similar to the Planck length?
Yeah. Well, it's a good question, of course, and I don't know the answer. When I first started thinking about atomic clocks, and people that I knew who were working on atomic clocks were dreaming about how good atomic clocks might be. That is, what would be the ultimate limit of how good you can make an atomic clock? We used to throw around numbers like a part in 10 to the 18. We're already better than that. So what I'm getting at is that a part in 10 to the 18 sounded like a dream 40 years ago. And now we have it. And now the dream is a part in 10 to the 20th. I don't see any natural limit. The idea of, say, Planck units, I don't think, well, first of all, the Planck time is so small that it's certainly not going to affect the kind of metrology we do. And the Planck length is also pretty small. The Planck mass is way, way bigger than the degree to which we can measure masses. So in other words, one of the things I'm saying is, for most things, we're not close to being limited by the Planck length or time. And it's not clear that the Planck unit has anything to do with what the limits are, because we measure masses far better than the Planck mass is. So, so I don't see any natural limits of that sort. But the more you work on it, the harder it gets to do better, because you're using all the latest technology, and that means in order to do better, you have to develop a new technology. So so yeah, I don't know where the limits are. I don't think there are any fundamental limits, but there are practical limits. It just gets harder and harder to do these things.
Thank you. Now, I'd like to ask you, how does the definition of the Kelvin is related to how we actually go to measure temperature?
Yeah.
I prefer to ask you about the time of flight measurements in the context of cool atoms and other temperature measurements that I think you were involved with.
Yeah. So, well, those were a number of questions, all good ones. So the way in which we measure temperature today, I mean, the way in which I've used this term a number of times before. Maybe I should explain what I mean. The way in which we realize the Kelvin. It's a technical term to realize the definition of the Kelvin. What it means is to bring into reality the definition. And the way in which we're going to realize the definition of the Kelvin today is the same as what we did before. Namely, we're going to use ideal gas thermometers. And now things are a little bit different in that we have defined what the universal gas constant is. So that means that if I measure pressure and number, and I know what the temperature is. So, but I'm going to use the same apparatus. It's going to be the same ideal gas cell that was used in the past. But the definition, this new definition, encourages us to think about new ways. So what I dream of is the following. I dream that we will have a gas of atoms, and we will shine a laser into that gas of atoms, and we will use the laser to measure the Doppler shift of some transition in that gas of atoms. And by measuring the distribution of velocities, using the laser to measure the Doppler shift, we will effectively measure the temperature, because the new definition defines Boltzmann's constant. And what Boltzmann's constant does is it tells us what the scale of the Maxwell-Boltzmann distribution of velocities is. So if we can extract the temperature from that, it'll be something that is a more fundamental way of getting at the temperature. And that's what I'm looking forward to, because being sort of a laser guy, it's the kind of thing that I like to think about. Now, I mean, obviously we can do that today, we just can't do it well enough. So what it means is we're going to have to work harder on doing laser Doppler velocimetry. And I'm eager to see how that works. I think we can do better. I think we'll be able to make measurements of temperature better than what we've been able to do so far. I'm really looking forward to that.
Excellent. Thank you very much. Now, could you explain how you came up with the ideas that led you to the contributions for which you won the Nobel Prize?
Well, okay, so this is getting a little bit off the subject, but that's okay. When I was a postdoc I'd finished my PhD, and I'd done some experiments in which I'd measured the velocity distribution of atoms after they scattered off of other atoms by using laser Doppler velocimetry, okay? Just the thing that I was telling you about now. And so I was thinking about the idea of connecting the Doppler shift and laser. I'm not quite sure why my clock is going off, but I think that maybe some other day I had something going on at 8 o'clock. Anyway, so I had this idea of connecting, measuring the velocity distributions with examining things using lasers. Then I was reading a lot of papers in the scientific literature, and I read a paper. Actually, there were two papers that really caught my attention. One of them was by Dave Weinland. Now, Dave Weinland won the Nobel Prize in 2012, I think, for doing things with single ions. But in order to do those experiments, he had to develop laser cooling. So he did the first experiment on laser cooling in 1978. And I read that article in which he described how they'd done laser cooling. And they'd done it to try to make a better clock. They weren't quite making better clocks yet, but he has now. So 1978, I read this thing about laser cooling, and I thought, that's really interesting. And then I read another article by Art Ashkin, who got the Nobel Prize just 2 years ago for something else. And he described the idea of laser cooling an atomic beam of sodium by shining a laser beam in the opposite direction. I thought, wait a minute, I've got a sodium beam right here in my lab because I was doing experiments with the sodium beam, and I got the laser that can excite that sodium beam. I can do this. I can do what Ashkin is proposing in this article. And so I went in the lab and I got the sodium beam going, and I got the laser beam going in the opposite direction of the sodium beam, which is the idea of slowing down the beam. And I looked into the apparatus, because the great thing about sodium is you can see the light. It's yellow. So many of the other atoms that we deal with, the light is invisible. But with sodium, you can see it. And I looked in there and I thought, this is harder than what Ashkin thought, because I could immediately see that all kinds of things were going on, optical pumping, and the atoms were slowing down a little bit and getting out of resonance. And I immediately realized that what Ashkin proposed was too simplistic, but the idea was golden. And so I spent the next 10 years trying to do what Ashkin had proposed and figuring out how to fix all of the difficulties that Ashkin hadn't thought about. And I think it's kind of interesting that all these people, Dave Weinland was not only the first person to do laser cooling, he was also one of the first people to propose laser cooling. He and Damelt proposed laser cooling in 1975. Ted Hench, who got the Nobel Prize in 2005, and Art Shallow, who got the Nobel Prize maybe in 1983, I'm not sure, also proposed doing laser cooling. And then Art Ashkin proposed this experiment for using laser cooling to do these things. All those guys who proposed and did the first experiments in laser cooling got Nobel Prizes for something else. So how cool is that?
Excellent. I know it was a bit off topic, but thank you for sharing with us that story. Now, if it's all right with you, we have time for a couple more questions.
Sure.
We have now more on topic. How do you think we may measure things? The way we measure things will change in some years.
Yeah, well, that's a good question. Well, one thing that's for sure, and that is that the way in which we measure time is going to change. So since we have the question, I'm going to go to my, let's see. Okay, so here, let's see if I go, here is a picture of Junyi and Anna Maria Ray. And an apparatus where in Junyi's laboratory, that little thing is a ball of strontium atoms, cooled down to within a few micro degrees of absolute zero. And here is a cartoon of how he traps those strontium atoms in what we call an optical lattice, a kind of an egg carton. And along with the theoretical help that Anna Maria gave to figure out how to deal with the fact that these strontium atoms talk to each other, he's made a clock that has a performance of 2 × 10⁻18. And here is Dave Weinland, whom we've talked about, and he's got a single, think of this, a single aluminum ion that he can measure the frequency of, and that accuracy is better than a part in 10⁻18. So this is going to change how we measure time. We're going to use optical clocks. We're going to use frequency combs, which I haven't talked about, but that was another Nobel Prize, to be able to translate these optical frequencies down to microwave and radio frequencies. This is how we're going to be measuring frequencies. We've already started to see this change, and sometime probably within the next 10 years, the definition of the second will change. And I think that we're going to start to see compact optical frequency standards. At least that's what I'm hoping for, that we're going to see compact optical frequency standards, just like we've got compact microwave standards now. And so this is going to be revolutionary, and we're going to do all kinds of cool physics, testing general relativity. It's just going to be so wonderful.
Thank you. Now, for the final question, how are you sure that these constant measurements are accurate? I'm sorry. How are you sure that these constant measurements are accurate if your measurement instruments are calibrated with the old system?
Yeah, well, okay. So it's an important question to make sure that they're accurate. Let me show this picture of the world. So yes, in the old system of units, the same experiment that today, say, realizes the kilogram, that same experiment was measuring Planck's constant. So it wasn't, so we were using the old system of units. It just meant that what we were measuring was something different. In the old system, we would measure the velocity of light, like people like Michelson measured the velocity of light. Today, that exact same experiment is called realizing the meter. So the fact that we were using a different set of standards just meant that the experiment was called something different. But now how do we know it's right? The way you know it's right is you get different people in different laboratories in different countries to measure the same thing. And if they get the same answer and they used different techniques, then you figure, okay, we probably did this right. And they did. Some of these people were using the silicon sphere to measure Planck's constant, and some people were using the Watt balance, and they got the same answer. The fact that you would get the same answer for Planck's constant by something that's an electromechanical balance and something that's a sphere of silicon, and there's more to it. You also have to do some atom interferometry to measure the mass of an atom in kilograms. That you would get the same answer using two so different things really gives you confidence that you've made the right measurement. To me, it also gives you confidence we understand physics.
Excellent. Thank you. Now, before we give the final remarks, would you like to say something to all the physics students that are watching you right now?
Sure. So, to the physics students, a lot of people ask me, what's your advice? And a lot of people will give the standard advice, work hard, don't give up. And all that is true. It's absolutely true. But I think there's something even more important, and that is never lose your curiosity. Remember what it felt like when you were 5 years old and you were curious about everything. Keep that as being part of what you are as a student of science, that curiosity about the way things are. That's the most important attribute of a science. of a scientist is to stay curious.
Thank you very much. I hope everyone listening to us will remember that advice every day of their careers. Now, once again, I'd like to thank you for from everyone in the organizing committee, everyone in the student body association, and all the teachers, all the faculty, all the students that came here with us today, for giving us a bit of your time, a bit of your, I'm sure, busy schedule. And we hope that one day we have the opportunity to welcome you to our campus and talk to you in person. Thank you very much.
I hope so too. It's been a pleasure.
I will stop the live stream.